Okay, well, I'm gonna get started. So this exam is from spring 2017, and I'll probably put the link to it in the description of the video, but I'm also gonna send it over through the chat. That way you can have access to it now. Right, and so let's just run through. I think this is about 7 pages. So I'll do like 4 pages today, and then I'll do 3 pages tomorrow or Thursday. And like this, it should be somewhat representative of it of the final exam. You can also look at other semesters. I just sort of picked this one because it's like one of the more recent ones, and in the other recitation, I'm doing a different semester, so you can maybe also look at that just as additional reference. But anyway, let's just go through this. So also, I'm going to be doing these things like off the cuff, so there's a possibility that I'll make mistakes calculation wise, but I shouldn't, and most likely I won't get stuck on anything, but we'll see. Okay. So for this one, you can probably, yeah, you can just plug this one in. So e to the 0 is going to be 1, and then the thing is going to be 1. So this whole thing is just 1. For this one, you're going to need to use L'Hopital. So this looks very similar to a trig limit, but it's different because of this theta squared instead of just being theta. And there's not really a way to recover that. So pretty much you do need to use L'Hopital's. And so in order to check that we can, we first try to plug in. We get 0 over 0, so L'Hopital's totally applies. So then we can go ahead and use it. So this is going to give me cosine of theta squared times 2 theta over 1. And then I can plug in. I'm going to get 1 times 0, so I get 0. Okay. Good. This integral looks pretty straightforward. So first thing I'll do is I'll write this as x to the 1/2, just to remind myself. So then the integral is x to the 3/2, and then reciprocate, so I get 2/3 in front. Integral of cosine is sine, and then the -5 is going to become minus 5x, and then don't forget the plus c at the end for the integral. For D, let's see, this one, we're taking the derivative of an integral. So this is FTC, Fundamental Theorem of Calculus, part 1. And so the only thing is that derivative of an integral, those two operations will cancel out, and then you just sort of change the variable inside. So instead of a t, it's x. And so you end up with this. For part E, this is quotient rule. So you just have to remember how to do quotient rule, which I will remind in case anyone forgot. Du prime minus ud prime over d squared, or you could, remember any other in a variety of different ways, just as long as you get the order correct for the subtraction, you'll be fine. So this is e to the x plus 5 multiplied by secant squared x minus tangent of x times e to the x plus 5, and then all over denominator squared. Okay. All right. F is just a product rule. So that rule I think everyone remembers. So derivative of cosine is going to be negative sine. And then notice that you actually have a chain rule attached to this part. So you'll have a 3x squared. And then we copy the other half, arctangent. of x, and that was all just half of the product rule. Next, we've got the other half. So I copy down the first half of the thing, and then I take the derivative of arctangent, which you should remember is 1 plus x squared. Right, so yeah, we kind of do expect you to remember the first couple of inverse trig derivatives. The next, number 2, limit definition of derivative. Right, so hopefully you can recall that definition. It's limit as h goes to 0, f of x plus h minus f of x all over h, and then you plug into this definition. Actually, for this, we want to specify it at 2, so I'm going to make some changes to this. Instead of x, we know like the particular value that we're interested in, so I'm going to replace the x's with 2. Okay, and let's go ahead and plug things in. So 3 times the 2 plus h quantity squared minus 3 times 4. Yeah, that should be fine. Over h, and then I'm going to expand this out algebraically. 4 plus 2h, no, 2 times 2 times h. So it'll be 4h plus h squared minus 3 times 4, all divided by h. And you see that there's the cancellation that you would normally expect. And also the remaining terms you can divide by h, so that'll simplify even further. 3 times 4 will be 12h, but then divide by h, so just 12. And then 3h squared divided by h is going to be 3h. Then we can take the limit, and so that's going to give us 12. And that should be the answer that we would expect. And for this, I may as well just double check that this is the right answer. So 6x evaluate at x is equal to 2, which gives me 12. So yeah, good. Okay. Right, so these are more advanced techniques for derivatives. So 3a is actually an implicit differentiation problem. It just doesn't tell you it, but that's what it is, since it's there's no way that you could solve this for y, right? There's no way you can make this some y a function of x. You can't describe it in that way. So instead you have to do an implicit derivative here. 2x minus, let's see, I'm gonna distribute the minus over. I'm just gonna take the derivative of x times y. That's going to be y plus xy prime plus, and then derivative of y cubed is going to be 3y squared y prime. And lastly, the right-hand side is equal to 0. Okay, so that was the step of taking the implicit derivative. Next, to do this, we need to solve for y prime. Okay, so I'll group everything with the y prime on one side and then everything without it onto the other side. This is going to give me a 3y squared minus x on one side, and then I will subtract over the negative y, so it becomes positive, and then the 2x becomes a minus 2x. Lastly, I'm going to divide to isolate the y prime. And as you know, y prime is just dy dx expressed differently. So there we have it. So yeah, all of this should be just kind of bringing things back into memory. Like this is like stuff from the first exam. Well, B might, I think B is also still the first exam, possibly, maybe the second. Oh, feels like it's been a while. Okay, so this one, as you can see, like the x in both the base and the exponent means that it's neither the power rule nor the exponent rule. for derivatives. Instead, what you need to do is you need to use the process of logarithmic differentiation. You need to take the logarithm to bring that exponent down, right? So ln of y is then going to be 7x ln of x. Okay, now that we've taken the logarithm, we can take the derivative, which I'm going to denote with a, oh, I don't need to say, that's a bit redundant, an arrow with a d. Okay, so the ln of y side becomes y prime divided by y. This side ends up being a product rule, so ln of x plus x times 1 over x, which just becomes 1. But then I need to move the y to the other side, and I'm going to move it over and replace it at the same time. I think I'll just leave the 7 the way it is, not distributing. So I just rearranged it a little bit. So 7y and then ln of x plus 1. So there we go. That's the derivative that I obtained. Okay. Pretty quiet. If you have questions, then just feel free to interrupt at any time. All right. So number 4 here, we're given the second derivative, concave, up, down, inflection point. So yeah, those are all information pertaining to the second derivative. So in order to describe this, it would make sense to start by drawing a number line for the second derivative. You see that the denominator doesn't contribute any zeros because it's always positive. The numerator does contribute a 0 at 3, okay? But it's also kind of like in reverse. So I know that on this side it's going to be negative, and this side is going to be positive, second derivative. Yeah, that's right. Okay, so then that's all I need to answer these problems. So concave up is the corresponding to the second derivative being positive. So this is, oh, not 0, minus infinity. This is going to be minus infinity up to 3. Concave down is going to be 3 up to infinity. Oops. And then inflection point is, well, it's just going to be when the second derivative changes in concavity. So for this problem, it's actually quite simple. In the other exam that I did, it's actually more complicated. But yeah, here it's just the x equals 3 because the concavity changed from one side to the other. Disappointingly simple, I would say. But this is all at 1 point, which is also kind of surprising. All right. Anyway, number 5. All right, so this one looks like a U sub problem. I don't know if that was immediately obvious to the to you, whoever's viewing this, but right when I see this square root and then the ln inside, I'm immediately led to thinking about letting u be the inside function. And then we see that the derivative is going to absorb the over x in the denominator. So this is indeed a good choice of u for our u sub. So the replacement we will end up getting is the square root of u du, which I would then think of this as u to the 1/2, and integrating it is going to give me u to the 3/2 times 2/3, and then we would back substitute this. So you 2/3 ln of x raised to the 3/2 power, and then don't forget the plus c at the end. Maybe I'll box this as well. Okay. B looks, this is also a U sub problem. Yeah. Yeah. So the fact that you see sine and cosine, and you should instantly, one of the things you should think is that derivative of sine is cosine. And so if you let u equals sine, of theta, then this is going to simplify to the integral of u to the fourth power, right? Du ends up being the cosine of theta d theta. So this is a good substitution to perform. We get u to the fourth du. But since it's a definite integral, we also have to convert the limits over. Or we could just say not to, but then we would have to evaluate. We'd have to back substitute to get back to the theta world and then evaluate in the theta world. Either way, we still have to do things involving these trig values. So we may as well sub out or switch over the limits, I guess. All right, so if theta equals 0, sine of theta, sine of 0, that's going to be 0. If theta is pi over 2, then the u will be sine of pi over 2, which is 1. Yeah, it's 1. Okay. And so we can now integrate this. We get u to the 5th over 5, and then we can evaluate that, 0 to 1. And so that's just going to be 1/5. Okay. I think I did that right. All right. How many pages are there left? Did I? 1, 2, 3, 4. Okay. Maybe I'll do. Yeah, I'll do one more page, and then I guess next time we'll have 3 more pages to go over. This feels too short compared to the other exam that I went over. It's also structured pretty kind of differently. I don't know which was more representative, but yeah, feel free to look at both. Okay, find the area bounded between. So this is stuff that we've just been doing actually in recitation. This is an easy version, I would say. You need to figure out where the intersection points are, but they're pretty straightforward to figure out. So y is equal to x squared is your standard parabola, and y equals 4 is just a horizontal line at 4, and you know that they would intersect at 2 and at, that's kind of off where I wanted to put it, 2 and minus 2. To find the area bounded between the two things, well, that's going to be that shaded region, and the way we integrate it is we take the upper function minus the lower function, and so that those are going to be the that will measure the height or the size of the height of the rectangles in between, and then we would run our rectangles from -2 to 2. By rectangle, I'm talking about the rectangles for integration, right? Meaning like the Riemann sums that you could imagine. So we integrate this guy, and that'll give us the answer. So we have 4x minus x cubed over 3, evaluate from -2 to 2. Don't really like this calculation, but it's still manageable. 8 minus 8 over 3 minus -8 plus 8 over 3. It looks like these will double up, so I'll get 16 minus 16 over 3. Is that right? Yeah, I think so. 48 minus 16 over 3, I think. Yeah. So that's just 2 times 16, 32 over 3. All right, well, hopefully I haven't made an arithmetic mistake there. There's a chance that I could have, but I'm pretty confident that's right. Okay, and number 7, find the volume of a solid, rotating the region bounded by x and, oh, I think this is a trick question, actually. This is one of those trick question things, because the second intersection point, I think, is not where you expect it to be. And it could be wrong, but I sort of see it. No, this is too easy. I was thinking of something else. So, yeah, it's something. I mean, yeah, you just draw it like that, I guess. I mean, I need to make this much wider to actually make things visible. Sorry. Okay, so 1, and you've got that shape intersecting at 1, 1, and at 0, 0. And you want to rotate it around the x-axis. So that's this axis there. And, well, which method do you want to use? Well, the easier, it turns out you can use either method here, but one method will involve a slightly larger amount of work than the other, right? It would be a lot easier to just use the functions as they are given, which we can do if we pick that red segment, which means that we're using a washer method in this case. So this is a washer problem. So you've got a pi on the outside, you integrate from 0 to 1 dx, and you have big radius squared minus small radius squared. Right, so you should have those kinds of formulas for volumes of revolution. It's a good idea to have them memorized. So big radius is the x function, so we square that. And small radius is the x squared function, so we end up squaring that, which is going to bring it to the 4th power. So this is the integral that will calculate our answer. And we go ahead and compute it. X cubed over 3 minus x the 5th over 5. Why does this feel like the same problem that we did on the homework? Maybe it is. Plugging 1, plugging 0. Okay, so yeah, 0 doesn't give you anything. 1 is going to give you a third minus a fifth. 5 minus 3, 2 over 15, 2 pi over 15. Yeah, I think that's right. Okay. All right then. So that's half of this exam. Are there questions? Anything you want to talk about or go over?
Oh, okay. Is there any way you could go to 5B and go over that really slowly? I have a really hard time understanding like the U and the DU.
The U and the DU.
Yeah. So like in this, I understand how you got sine as your U.
Okay.
But why'd you go from 0 to 1 and not 0 to pi over 2? How did you get that change?
It's because these limits apply in the world involving theta. Okay, so these are corresponding to theta equals 0 and theta equals pi over 2. So when we want to convert the whole integral over to being represented in terms of u, what we need to do is we need to convert those limits over. So what I did is those values are saying theta is equal to 0. What does that tell us u has to be? And what the way that we convert it over is we use the u substitution to calculate what the corresponding values would be. So the two limits are 0 and pi over 2. What are the corresponding u values going to be? And it turns out when we plug those into sine, we'll get 0 and 1. Then you end up putting those back on your integral so that you've converted everything over to the u world, not just the integrand, the thing inside the integral, but also the limits. Does that answer your question?
Yeah, that actually makes more sense. And then, so when you went from u to the 4th du, how did you go from that to u to the 5th over 5? Like what happened? Why'd your du go away, basically? You see what I'm saying?
Well, that's the process of integration. So u u to the fourth is the function that you're integrating over, and du is just the closing thing saying like this is the function, like everything in between the integral and the du, that's what we're integrating, right? So it's just like a closing statement. And then all you do is, well, we're using reverse power rule to figure out that that is the antiderivative of u to the fourth.
Okay, I see what you're saying. My question is, okay, I think I'm just looking at this wrong. So you had sine, so your sine to the 4th cosine, right? And then you put your u as the sine, but where did the cosine go? That's what I'm confused about.
So that comes with the converting over from the u sub. So what happens when we compute the u, when we choose our u for the u sub, we also need to make the du that we get, we need that to kind of be reasonable to sub away. So what we do is we take the derivative of the equation. So u is equal to sine theta. I take the derivative and I'll get du on one side. On the other side, I get cosine of theta d theta, right? This is kind of a related, not kind of a implicit derivative type of thing. It's around that section. So does this step make sense?
Yeah, I understand that.
Yeah. Yeah. So both of these things are part of our conversion over from the theta world to the U world. Both of these are what I would describe as being the U sub process. And so you see that this is this matches the du. This is exactly du as described. So that's why the cosine disappears. It's because it gets absorbed into what we define, what we call du. And then this guy, as you see, like sine raised to the fourth, well, sine is u, so then this turns into u to the fourth. It's just a part of the u sub.
Okay, that actually makes a lot more sense. Now I
Mhm.
understand what you're saying. Thank you.
Yeah, yeah. I mean, if you still feel tripped up about this, I can recommend like looking at some things by Black Pen Red Pen where he like goes over some u sub type stuff. Um, yeah, it might be a good idea to like look at some of his videos or go through like one of his worksheets if you want to practice as preparation for the exam.
You
Um,
said black pen, red pen?
yeah,
Okay, sweet.
yeah, I can try to look that up right now while we're here. Mm, yeah, his like Calc 1, what you want to look at are primarily like the stuff within Calc 1 because he has a tendency to work on like much harder integral problems just because integrals end up being more interesting. But that's when you get to like Calc 2 level material. Let's see if this will. Yeah. Some of these might be a little bit too challenging, but or otherwise like the, I don't know. If you want, I can try to look up some additional U sub problems. Or we could try to talk through some of the things. If not, we could also just end a bit early.
I had uh, the last thing we were going over. It's the disk method, right?
Okay, yeah, those things. Yeah.
Are we, or the shell method? Are we gonna be over that next time? That's something I'm
Um,
tripped up on.
I don't think that'll show up on this exam,
Okay.
but we
So
can talk about it. So yeah, I can grab a problem. We can talk about that now. It looks like the second half of it doesn't do volumes revolution.
Can I pull up one? There was one I went over on the online homework that
Okay.
just, I don't know, it just confused the crap out of me. Hold on. I think I can still pull it up. Yes, I can.
Yeah,
Okay.
sure. I'll stop
So
my share, and if you don't mind, like keeping it in a recording, like we can also just do that. Otherwise, I can stop the recording.
yeah.
But
Okay. Can I read you mine?
oh, you could just share the screen with me.
Oh yeah,
But
yeah,
or yeah.
yeah. I have a lot of screens. Let's do this one. Can you see that?
Um. Okay. Yeah, I see it now. Got it.
Okay.
All right. Uh-huh. Um. Find the volume of the solid generated in the region enclosed by the given curses revolve around the x-axis. Okay. So you got the right answer. But you don't remember how you did it.
Yeah, I figured it out, but it was just like, I mean, I got it right, but
Mhm.
at the same time, I did not feel confident. I also went
Okay.
to the tutoring help for this one,
Sure.
and I still like really
Okay.
had no idea.
Yeah, sure. I mean, no, it's no problem. Like, well, yeah, let's talk through it. Um, I'm gonna just annotate on top of it if you don't mind.
Okay.
And the only thing is, like, I don't know if this will show up in the recording or not, but we'll just have to make do. So cylindrical shells. So you should remember the formula. Let's write that down. 2 pi integral, and it's going to be a radius function times a height function dx, right? And I typically need to graph something to actually visually inspect what's going on. X equals 5, okay, is going to be a line like this, and we want to rotate this about the x-axis. Use cylindrical shells to find the volume of this. Y equals 0. That's a little bit weird because, like, the default way I would do this is probably using disk method, since this is perfectly set up to use disk method. Um, but we can certainly try to use shell method. The issue is that we have to tilt things sideways to make that happen. See, what happens is that the segment that you need to draw cylinders is you need this segment that's like parallel to the x-axis. Um, which means that how do I want to describe this? It means that also the way that it sweeps over is going to be different as well. So it will go from y equals 0 to whatever this value is. So if x is equal to 5 here, y is going to be the square root of 5. Okay, I'm pretty sure. We'll find out if I make a calculation mistake, since you have the value that we expect to get out of this. So the function that we would see in this case, it would be 5 minus the square root of y, right? So what happens is that you have y equals x squared. In order to tilt things sideways, what we need to do is we solve for the other guy. So we end up with square root of y is equal to x. That gives us things as a function of y rather than a function of x, which is necessary because our integral for this problem is actually going to be in terms of y, because like the problem wants us to do things using shell method. And so now we have 0 to root 5. Now we have a 2 pi in front. Okay. Are you following so far? Does it make sense what I'm doing so far?
Yeah, this makes sense.
Okay. And so now now that we have the integral set up, we just have to check and see, like, does this evaluate to give the right quantity? Minus, and this is y to the 3/2 2/3 plug from 0 to √5. I don't like this number. That really, I'm getting the suspicion that this is actually not going to give me the right value. Let me just
So
shortcut this.
so what
Check.
I did
Yeah.
was I went from 0 to 25. So I just took like this, I just squared 5, and that would be like your total height of it, I guess.
Oh, yeah. No, that's right. I don't need to take a square root there. That's supposed to be 25. That is absolutely correct. Yeah, the corresponding y value is squaring the thing, not square rooting the thing. Okay, that might resolve everything then. So this goes to 25, this goes to 25. I take a square root of that. 625 minus 2/3. Um 625. 1/3 of 625 times 2, though. That's what I end up getting. Yeah, so I'm still not getting the right. I'm not getting the same value. I think I end up getting 625 pi over 3 times 2. The integral that you set up is the same.
So mine was I was seeing if this would be the same. I was having a hard time following. What mine is it's 2 pi from 0 to 25, and then it's my either my radius or my height was one was y, and then the other was 5 minus y.
Oh, you know what? Yeah, one was okay. You're right. I forgot the radius. The radius is going to be y. This value is the height. I forgot to put the radius. I'm blanking on such basic things. Okay. Let me. Don't like this annotation software. But yeah. Right. So then when you evaluate this, and that's exactly what you said, right?
Yeah.
Okay. Plus y to the 5. 3, so 5/2, 2/5. So you don't need me to do the rest of the integral. I'm convinced that this is going to work now. Yeah. Yeah, so I don't know. I was a bit sloppy with my explanation. I don't know if you feel like you understand it any better.
I think kind of looking at it differently, I guess, kind of helps me like understand it a little more. You can see I attempted this 13 times, so it wasn't easy. And then can I go to the first one? This
Yeah,
one.
sure.
So on this one, it's if you draw it out, it looks the same as the last one we just did, but it's it looks
Okay.
the same, but it's not. I had to do it differently, and that's where like I was really getting confused on these.
Okay. Let me try. Yeah. I opened Mathematic up so I can double check my answer afterwards. So, yeah, so x cubed, x is equal to 4 and y is equal to 0. Yeah, so it's still that. Oh, but no, you're revolving around the y-axis this time, so it is different. In fact, this is, I think, yeah, this is the more standard thing which would look like a shell problem. So I don't need to solve in terms of the other variable for this problem, just because the axis is set up differently. So let's see, in terms what the integral I would get here would be 0 to 4 dx. Radius is just x. The height is going to be x cubed. So let's see that if I get the same value. So integrate x to the fourth from 0 to 4. 2048 over 5 pi, yeah. Yeah, so this is the way you do it. Well, that might have been a little bit fast. Let me know if you got confused by anything here.
Sorry, I was looking over my work.
Mm.
No, I see what you did. I'm trying to see what I had for my radius x minus 4, but oh no, I redid it. Yeah, I redid it. Never mind, I was wrong. All right.
Yeah, I mean, usually you're not gonna have something like x minus 4 as a radius, because what that will do is it will it's like you're sweeping over the domain, but like in the reverse order. Like one way you can kind of try to think about it is that you like pick out a specific x value and you check like say like x equals 1, or for example, then like for that particular um segment, you want to make sure that the height is the thing that you'd expect and that the length is the thing that you'd expect. So you'd expect this to have the length 1, and you'd expect that the height would be 1 because it's 1 cubed. And then you can check like everything else. When you say something like 4 minus x, that's really reversing the direction that you're sweeping over. And so usually that won't happen. Maybe it could happen if your axis of revolution is off center, but it would have to be off center in a kind of a very special configuration, I would say. Yeah. Yeah. I don't know. Anything else you want to go over with this?
I think that's it for now. Yeah, I think that's it for now. But thank you.
Yeah, no problem.
I'll stop sharing.
Okay.
That's all right.
Yeah. Sure. Right. So, yeah. If there are any other questions, like we can go through them. Otherwise, guess I'll see you on Thursday.
Thank you.